So let me back up then and go to a mathematical explanation with a graph. So what we have here is a graph of, typically would be x, y, but here we have n, where n is on the x-axis. If our program depends on n, and it outputs n, so if we take n as an input and we do n number of things, then we have a simpler, what's called a linear function, and it's of order n. If we do something that's of order 2 of n, this increases very, very quickly. If you simply plot these functions, log of n increases very slowly, a lot less than n. 2 to the n increases extremely quickly, and n is linear right in the middle. Page 107 of your book is a particularly good one to flip to. What I've done here is copied off the last line, adding to the 1, to notice what happens when you get various inputs. So back to our for loop example, if we have a value of 256, printing 256 i's, this is O of n, like we've talked about, because it depends exactly on the number of inputs. Then this will run 256 time units, let's say. But it's dependent on n. Now, I don't have great examples for you of all the different ones, and we're going to go through them in the class as we get further. But I wanted to give you a couple of them. So this is a O of n squared function down here. Actually, let me back up 1 second and explain further this whole fudging into categories thing, because I don't think I quite finished that up. So if something is just a bunch of statements, it's not dependent on n at all, then we throw it in this O of 1, which is actually all the way down here, which is beyond the axis, actually. It would be a value of 1 always, and it would just sit at the value of 1, which would be right above the n or x-axis. And this doesn't take any time at all. Now, we don't really care if it's 2 or 3 or 5, because most of our programs are going to be driven by the value of n. And the reason why this is because, especially in graphics and in gaming, we have huge, huge inputs. Imagine you're rendering a screen or doing something that I'm sure you've done for your other classes, where you have millions of pixels, 10 million pixels, etc., or 10 million objects on the screen, and you have to do something, collision detection, rendering, what have you. Then you're going to run through some kind of loop or some kind of algorithm, and you're going to do that for each, say, item. So the order of that operation of that function that you've run is dependent on the number of inputs. So for very large numbers, for very small numbers first, what you have to understand is these numbers all in here that are very tiny, for values of 1 or 2 or something, they don't really matter, because it's going to be quick no matter what. Even if you have a 2 to the n function, some horrible, horrible algorithm that's written extremely poorly, it's still going to execute very quickly for an input of 1. But if you have 10 million inputs, then the numbers start getting crazy. And that's where we get concerned. And that's why we talk about we're only concerned with the large values of n. We're not concerned with small values of n. Well, mathematically, if you're not concerned with small values of n, you can just chuck them off. So if you have a mathematical function n squared plus n plus 1, we don't care about the 1 factor. We don't care about the n factor. We just care about the biggest term, mathematically speaking, because this is going to drive the number much more than these other terms. It's kind of a little bit of a wavy-hand mathematical explanation, but that's essentially what happens. So now, back to this example here. This is an O of n2, n squared function, and what this is a loop inside of another loop. So we're going to do something n times, and then inside the loop we're going to do it n times again. And we're just going to do a simple summation, but it doesn't really matter what we do in here. This runs n times, and then this runs n times. But notice that this loop is inside of that loop. So each time this loop runs, it's going to happen n times. So what that means is you have n times n, which is n squared. If you had a third embedded for loop in here, that was dependent on n, because remember, if it's not dependent on n, then it doesn't matter, then it would be n cubed. And that's how you get these squared and cubed terms. Log terms, we're going to wave our hands at a little bit now, because we're going to cover it really well later when we talk about binary trees. But for those of you familiar with a tree structure, what you can do is you can actually decide whether you're going left or right when you traverse a tree, and then you can chop off half of the nodes. So when we decide to go left, we can ignore all these over here and get rid of them. And now, once we're here, we can decide to go left again and ignore all this over there. And we can chop down the tree, basically, by a log value each time. We'll go over this a little more later. It's not important right now, so don't worry about it too much. But that's how we get these log values, so we can have log runtimes. And what you need to know for the class is basically to be able to identify whether you have an order of one kind of operation or algorithm, like a simple statement like this, or whether you have a n-dependent operation or a loop. And you have to be able to tell at a basic level what these things are, so that you can, so you'll understand the basic runtime of an algorithm. Now, again, back to this table. So I want you to understand the impact of these numbers. When you have a function that's dependent on n, that's a linear growth. So 256 inputs, 256 time units that it takes to do. If you have 10 million items that you're rendering or doing something with on the screen, 10 million time units it will take. That's a long time depending on what you're doing to it. And that's where the problems get in. So once it gets bigger, n squared, this is 65,000 just for a value of 256. And cubed, 16 million. And 2 to the n, if you're so unfortunate to have an algorithm of this type, is more atoms than exist in the universe. This is a number that we can't even write down, it's so big. That necessarily means that if you wrote a program that took 2 to the n time, and there are no great examples, particularly for this reason, that it will just never complete. Programs that never complete are not very useful. But you have to be able to identify when your program is never going to complete. This is the obvious case, but even if you have an n-cubed algorithm, let's say, and you have 10 million inputs, this number is never going to complete either in most algorithmic cases, no matter how fast a computer you run it on. Computer speed is one thing, but if your inputs or your complexity of your algorithm is such that it is so big that it will never, or so big that it's going to be running in, time units that you can barely even write down, then of course it's never going to complete. And that's the important concept that you have to understand here. The other kind of interesting / tricky thing to be careful of is when things combine. So in this example, like I told you, this whole example is O n squared because there's a loop inside of a loop. There's also a cout statement at the end here, and this is O of 1. So you have to break this up into components. So this inner loop here is O n, and this outer loop here is O of n, and this is O of 1. And if you have another statement down here, that would also be O1, O1, O1. If you add all these up, those would be O of, doesn't matter, O of 5, which equals O of 1, because it's still not dependent on n. Now this happens, inside this loop happens n times, so these two have to be multiplied. So O of n times O n squared plus 1. But O of n squared plus 1, or plus 5 even, is O of n squared, because we just dropped the term off. It's not important, it's not going to drive the whole overarching value of this. These are all big O's, by the way, of course. And so, even if you add a simple constant statement to this, it's still O to the n squared. It's driven by the highest factor. I've said that several times, but it bears repeating because it's important. Now, there's other things you can look up, and we might talk about a little bit. Besides big O, there's theta and small o, which are other determiners of time. So big O is a overarching highest value of. The others can give you a more exact range or a smaller range, which is important in theory and in mathematics. But in our case, all we care about is it's not going to be worse than this. So big O is a worst case running time, and that's what's really important here. We want to make sure that no matter what inputs we have and what our algorithm is running, it doesn't get worse than this kind of time. We have to be assured that there can't be a worse case than we're already calculating, because we have to be assured as data structure specialists so that we can tell the world that our algorithm will complete. For example, if you write a game and you can't iterate to somebody or explain to somebody what the order of the runtime of the algorithm is, and how do you know if a program will ever complete? It might just go on forever. Meaning it might sit as a loading screen forever. It might not render the screen. It might crash on the user because we use infinite memory. We usually talk about big O in terms of runtime, but big O can also be used to talk about memory, to talk about any other aspect of computing. But we tend to care less about those because the time is usually what we're most concerned about. But that doesn't make it the only important factor, of course. That's all I have to handle for now, so I'll stop there. And please do ask questions, and I hope that's been helpful.